I've made a small list up here. You can copy this down. I commonly will write things on the blackboard or whiteboard, just so I don't forget to talk to you about everything I need to talk to you about. I have a terrible memory. We'll end up using that against me, I'm sure. You told us you were going to extend the homework. I won't remember it all. Anyway, let's see. There's homework due, what, next class, I think? So how's that going? How many people started it? How many people are finished with it? Right. Those of you that are finished with it, was it easy or hard? Easy. If you have any questions on it, please feel free to ask. There's going to be some time in class that will be a little more free. I've got a couple things I want to show you. Logic Pro is taking its sweet time to install. There we go. Now this is there we go. Now you should be able to see the whole screen. So I'll try to get the blackboard. The main thing I need is Logic Pro. Okay, so if you have questions on the homework, please feel free to ask. But since Logic Pro has decided to start, we'll go ahead and jump in that. I want to show you a few more things. Last time we talked about comparison instructions. What you should have realized from that is that we have the ability to deal with numbers that are more than just ones and zeros, so more than just one on and off. We can deal with contacts, which are on and off, and we can deal with coils, which are outputs for on and off, but we can actually deal with whole words of data at the same time. We can perform a comparison instruction in order to turn on the traffic lights if the timer's accumulated value is above a certain amount. Just remember that. Anyway, counters are a lot like timers, so let me start by showing you some counter instructions and how they work. You don't always want to count time, which is what a timer does.
You can totally disable it.
I'm sorry?
You can totally disable it.
Where?
Settings, hide or enable merge.
Ah, thank you. I've never noticed that.
I'll just see it.
A for you. He's done.
See you later.
Okay. Anyway, thank you. That's very nice. I never thought to look for it. Okay. Let's see. So timers and counters are in the same tab because they're very similar instructions. In fact, if I pull down a T-on timer instruction and a count up CPU instruction, they look a lot alike. You have to give both an address. You have to give both a preset and an accumulation value. And the key thing, the only thing that's really different is that, of course, the timer counts up time, but it's counting in tenths of a second, so 0.1. So we get to choose the time base. Whereas the counter just counts events. So right now, the way the counter works is it has to see a pulse. If I were to run this right now, put addresses in and everything, the counter would count one pulse, even though the program keeps going back over that counter. It doesn't count a new count every time the program goes through because the program goes through very quickly. It's expected that, say, an input connected to this would be on for a long period of time, so it doesn't make sense for the counter to increment its count every single time it goes through the code. Instead, what it looks for is a transition from low to high. Okay, it looks for this transition. So technically, this is a rising edge counter. It doesn't look for the falling edge, it looks for the rising edge. And it waits for the falling edge in order to reset before it will count another pulse. So if over time, by the way, there's time here. If over time, instead of doing that, if our signal goes like this, then it'll only count one transition, one rising edge transition. Okay? So let's play with this and see what happens. Let's start off with the I/O simulator because it's easy with the I/O simulator to show you how this thing works. And then we'll apply it to the bottle line simulator. Normally I don't use those as examples, but if we're going to program the Christmas display this year, well then I can use the elevator and the bottle line as examples. So anyway, we've got to give it an address. So I will give it an address in the counters file. Now the counters file is C. I don't remember the number. It doesn't matter. It's redundant. So C:0. First counter. It's file 5. There we go. I couldn't remember. And I'm going to let it count up to 10. Once it has counted up to 10, then it will be done. Now let's play with this just as it is. Like I said, what it's going to do when I run this is simply increment its count by 1 and sit there. Why? Because the preceding rung up to the instruction is true. And so all it has observed is that the program started, therefore there was a transition from off to on. So it's just sitting there waiting for the falling edge before it counts another rising edge. Okay? Now the program, it's going through this line over and over and over. So it's looking at the line, it's going to the instruction to see what it should do. It looks and sees that this has not changed from 1 to 0, so it does not count it. So let me add in something to make this a little more interesting. What about if we add a switch in? Let's just grab a set of contacts and hook them up to, let's see, grab the switch. So let's call this button to be counted. Okay, let's call this button counter. Really original today. Now I'm going to change this to a momentary switch. And the way I did that, if you're wondering, is I right-clicked on it. You can right-click through it and cycle through the different types of switches. So let's download that and run it. Now the counter is already at 1. What that tells you is that these counters are retentive. They don't just lose their count when the PLC quits, okay, when the program quits. So in memory somewhere there's a 1 that has been counted. Now if I start pressing that button, it's wired to this set of contacts, and that set of contacts is going to go true. And it's going to send a rising edge pulse, because right now it's off. Right now, the signal going into that counter looks like this. And the PLC over time just keeps looking at it and looking at it, and this is all it sees, is that it's off. So there's no event to count. So, now I'm going to hold down this button. When I hit it, I'm going to hold it down. Watch when the count increments. Are you ready? I'm holding it down. The count incremented. See that? I haven't let go of the button yet. The reason it incremented is because it saw a low to high transition. Now, when I release it, now it's ready for another pulse to count again. So as I click the button, the count just continues to rise. Now, over here is a CU, that stands for count up bit, and all it is, CU is the bit associated with this counter that goes true whenever the run preceding it is true. Now that's handy because sometimes you want something to be triggered when the counter is triggered, and you can use the count up bit to make that happen. I'm going to modify the program again, and I'm going to make a light come on whenever the count up is detecting a low to high transition. Okay? So let's grab a set of contacts. We will reference the count up bit. So C:0, that's counter number 0 / CU for count up. This is the count up bit. When the count up is true, this will be true. And so let's grab an output. We'll just use a lamp. Say this is the counter increment lamp. Okay? So not surprisingly, the counter keeps its old count. It's right there at 7. And as I press the button, you'll see that the light comes on as long as the button's pressed, and I release, and the light's no longer on. Now what do you think is going to happen when I hit the button one more time? Well, the accumulated value is going to go to 10, and so the preset accumulated value will be equal. Now there is a done bit, a DN bit on this counter, and when the accumulated value reaches the preset, then the done bit will turn on. Okay, so let me modify my code one more time. I'm going to add a set of contacts in here and an output lamp. This output lamp, I'll just use the address below, and I'll just title it counter done. Another way of saying that is accumulation value equals preset. That's not quite right, but we'll use that for now. C:0 /done. And we'll just call this counter done. Okay, now download, run. As soon as I hit the button, count done comes on, which is what we expected. Now what if I hit the button again? What do you think would happen? Well, it depends on the way they made these counters work, right? Well, it turns out the way that Allen Bradley does it is it will continue to count, but nothing really changes. Because really the comparison is if the accumulated value is greater than or equal to the preset, then the done bit is on. Okay, so right now our accumulated value is 16, preset is 10, and the counter is done because the preset or the accumulation value is greater than or equal to preset. So it's pretty straightforward. It's easy to use once you understand what the bits are for. Now, what can we use this to do? Well, I'd like to use this to count bottles going by on a conveyor. So let me go to the bottle line simulator. And I have to detect where bottles are sensed. Where's the sensor for bottles? Well, it turns out it's right here. This sensor, limit switch 1/6, is a sensor. And let me move the mouse off of it. The way it works is whenever there's a bottle in place, this gives a 1 at that address. Whenever the sensor is between bottles, it goes off. So this will give us a nice pulsing signal whenever the bottles are going by. Okay, now to get the bottles to go by, I will have to turn on the motor. So I'm going to show you a start-stop circuit one more time. Let's see, that just turns the motor on and keeps it on, and then we'll set it up to count bottles. So let's just make a new file rather than modifying the old one. We will build a simple latch circuit for the start-stop button. We have a structure for it. The address of the motor, in this simulator you can drag the address from the motor itself. If you hover over it, it'll show you what the address is, but I really don't care what the address is, I just want to use it. So I'll make this symbol conveyor motor. It's more of a label, but you can't address that label. Okay, so let's copy the address over here so that once it comes on, it seals in. We'll drag the address of the start button in here and the stop button in over here. As usual, this is a normally closed stop button. So you can see when I hover above it, it says NC, which means this normally passes power. That means that the instruction that references that button is going to normally pass power as well. So it will normally be true unless the button is pressed. And that's the way I want it to be. So let's right-click, edit symbol, stop button. Right-click, edit symbol, start button. Okay, now what this is going to do is when I press the start button, the conveyor motor will come on. When I press the stop button, the conveyor motor goes off. You've already seen this a few times. Start, stop. Now they're going by way too fast for me to count. Okay. Say stop. Okay, now I'd like to set up a counter to count those bottles since I can. So let's set up a counter. And the counter will simply be driven based on this limit switch, which the address is 1/6. I don't really care. This is the bottle presence sensor. Okay, so let's call this the bottle counter. I've got to give it a number, so I'll give it C:0. Preset, I don't really care. Let's just say I want to count up 100 bottles. Okay, for whatever reason, so I'll leave that in. I don't have to put that in. Okay, if I don't put that in, the counter will go up all the way to 65535 before it starts back over at 0. Let me show you why. If you look in memory at the counters file, you can actually see all the data associated with this counter. This is counter 0. Let me pull it down where I can reach it. This is counter 0. Here's the count up bit for that. There's actually a count down bit. I'll show you what that looks like in just a minute. There's a done bit, an overload bit. Okay. UN, I don't remember, I'll just be honest. I'd have to look it up. I've never used it. Okay. Whatever it is, if somebody knows, shout it out. Whatever. .pre is a whole word of data. This is the preset value. That's why it has 100 in there, because I put 100 in here. And then the accumulated value right here, that's what was storing. Remember we shut off the program and yet remembered how many times we hit the button? That's because it has a whole word of data that's dedicated to storing that information. Okay? And that information in memory is not cleared when the program stops. That's why when it comes back on, the instructions are still referencing the same memory location. So there's still an accumulated value in that counter. And you might look at this and say, you said count up, count down. What the heck is this? How do you get a counter to count down? I'll show you this one. Well, let's play with this and see what happens. Download, run, doesn't do anything. That's because we have to hit the start button. So hit the start button, and we're counting bottles. We're going by fairly quickly. And we can slow it down. We'll turn down the scan speed, which actually just slows down the simulation. A little too slow. Probably a little too slow. Of course, if we close this, it speeds up a lot. So you kind of have to play with this just to get it to operate at the speed you want it to. So So this looks pretty decent. You can see that every time a bottle comes by, the input is triggered and we're counting bottles. Now there's one problem with this. Notice that there's a bunch of broken bottles in the string. I don't want to count bottles that are broken because they don't add to the product, the number of products that I made or that are on. So what I'd actually like to do is decrease the counter by 1 for each broken bottle that I sense. Okay? So I'm going to show you how to do that. Now here's the problem. Students commonly look at this instruction and feel like that entity is the counter, but it isn't. This is just an instruction to increment the counter. The counter is really 3 memory locations. Okay? It's 3 words of data, and I showed it to you just a minute ago. Really, the counter itself resides here. This is the counter. These 3 memory locations together are the counter. There's 1 word of data that has more than just 5 bits in it, but here's 5 bits from that word of data. And there are 2 other words of data. One is the preset, one's the accumulated value. And those 3 words of data together really are what make up the counter. The counter is not this instruction. All this instruction does is increment the counter or make it count up. Does that make sense? I could have another section of code that, based on something else, also increments the counter. Okay? Now, that's not very good practice most of the time. It'd be better if I want to increment the counter for another reason, to have an OR around that. Okay? But anyway, in this case, I like to decrement the counter. So it turns out that there is an instruction for counting down. Now, what I'm going to do is reference the exact same counter. Because like I said, the counter is really something that is in memory. Okay? I don't want to change the preset. If I change the preset here, it will change the preset on the other location. Well, once it starts running, it will do it. And like I said, what's in memory is what's really important. So the preset is now 200. This one would update once I run the program. In fact, I'll leave it at 200 so that you can see that. Well, what I want to do is count down on the condition that the bottle broken sensor senses a broken bottle. Okay? Now they're off by what? 1, 2, 3, 4, 5 or so bottles, but I don't care. I'm just watching a string of bottles before 5. So if I increment it here and then decrement it a little bit later, that's fine. So let's look at the address. In fact, let me grab a set of contacts first. Okay, the address is, it doesn't matter, I'll drag it over. So let's call this the broken bottle sensor. Now whenever this goes true, it'll instruct this countdown to decrement by the way. Okay, now we're going to have to watch it in slow motion to see what's happening with this run. Start. Now let's watch. Whenever a broken bottle comes by, see how that instruction lines up? Okay, so we're watching this one. And wait for it, wait for it. Here we go right there. Okay, watch. There it goes. You see that? So every time a broken bottle comes by, this instruction is triggered. Now just to show you that this is working, I'm going to turn this one off for just a second, and you'll see the count be decreased. Okay? So program, let's just say I put another set of contacts in here, and the enter button has to be held down. We'll call this count up in our bottle. Yeah, count up in A. Right now it's not enabled. Unless I hold down the enter button, it won't be enabled. So let's download that and run it. Start. You'll see that the count is going down now by each bottle that goes through. So if I hold down the enter button, now we can count up bottles. If I let it go, you'll notice that the only thing active now is the countdown instruction. Okay? Do counters make sense? You see how counters and timers are really basically the same thing. It's just that a counter will count up based on events that are triggered on the run preceding the count instruction. And timers just add up time continuously when the run preceding them is true. Okay. Counters, by their very nature, are retentive, whereas most timers are not. If you use a retentive timer, it will be retentive. But counters are naturally retentive. And the reason for that is because most of the time you want them. All right, so this is not a terribly useful system. I haven't programmed a solution to the bottom line in what I've done so far. I've got one from before. I may as well go ahead and show it to you guys. I don't think you guys have ever seen the bottom line run completely, have you? Let me show you what a program looks like that, no, I did show you a student solution, didn't I? I don't remember. Well, let me show you a solution. Okay, 34. Let's see. I don't remember if I left my solution on the H chart.
Actually, I think.
Yeah, bottom line simplified. There we go. Now, I'm the world's worst when it comes to revising my program and revision numbers. So I can never remember which was the most recent version, which one actually worked. Let's see if I can go by the date. 3/12, that makes sense. 12:57 p.m., probably right before class started to actually finish the thing off. So that looks about right. So let's open up V2 and see if that works. Version 2. Okay, here's the program. Yeah, that looks like my program. I've used a bunch of jumps so that I can clean up the code a little bit and try to keep it from being too unwieldy. But there's the main code. It's 13 lines. And then I use several subroutines to make certain things happen. So anyway, I'd go through it and explain it all to you, but it's been so long since I wrote it, I don't really remember how it works. I'd have to go through and figure it out again. That's why it's so important to comment your code. You can see here I've made a mistake because I didn't comment some of this stuff. Some of it I commented, some I didn't. Anyway, let's hide my poor example of programming. Download, run, start. Okay, now it's initially filling bottles and you see spray going everywhere because it doesn't know anything. It has not detected these bottles. There's really no way to solve that problem unless you count, you don't allow it to start until a certain number of bottles have gone by. But anyway, I didn't worry about that part. I just figured I'd clean up the mess with the first few broken bottles. But you'll notice that the capper does not try to cap any bottles that aren't there because they're broken and they fall into this bin. You fill the tall bottles with the large fill, the short bottles with the purple grape juice or whatever it is for whatever reason. That's how we're building this stuff. And the sorter here at the end works also. Now, some students managed to make this part just a little bit nicer than I did. They managed to set it up so that there was no space between the bottles. And that was something I wanted to do and just ran out of time. And I couldn't figure out a good way to do it anyway, but they did that. And that was one part I was disappointed in my program for. But other than that, mine does a fairly good job. What you find is that a lot of times students will try to use timers instead of sensors to solve some of these problems. And the system is sensitive then to the speed at which it's run. So a lot of them you can't do this. You can't speed their code all the way up and just run and work. It'll start breaking bottles or overfilling and cause all kinds of problems. I was careful when I made mine so that I didn't, I avoided that problem. The key to my solution that most students did not figure out was that it's very important that you go from one bottle to the next stop and make sure all the stations are done before you try to go to the next. So I set up code to do that. In fact, if I remember right, my subroutines are set up so that each subroutine deals with a separate part of the system, okay? And basically, yeah, here it is. You can see all the done bits. Basically, I've got a bunch of different bits that trigger the index being done. Okay, so index just means the bottle is moved into position. And then I've got a bunch of bits from each of those subroutines that I set once that subroutine is finished. In other words, once the bottle has been filled or the bottle has been capped, each one of those has its own separate subroutine that sets a bit once it's done. Until all the bits are done, we don't try to index again. Okay? So just made sure that all the systems worked together, worked kind of hand in hand. And it solved a lot of the speed problems. I didn't really have any speed problems. Dealing with the displays wasn't easy because this is multiplex. For those of you in ECET, do you know what multiplexing is? So it's multiplex. So you can't just set the outputs for all these at once. One scan through, you have to set one and then wait. And you have to multiplex and choose a different bit. In fact, you have 2 bits you set, okay, because you've got 4 different displays. And then you write the output for the next, you set the bits appropriately, wait for that scan to go through. So you have to kind of scan, you have to go through each one. one at a time. So every 4 scans or so, these are updated, but it happens so quick by comparison to the user's eye, by comparison to the mechanical system, you don't really notice it. But anyway, I'll probably just go ahead and post this for you guys if you want, that way you can look through it, if you really want to dig through that much detail. Because if we're going to program the Christmas display this year, it'll be quite different from this, but you can learn something from this code. I think I set it up so that you can actually stop it and it remembers where it's at, and then you can, oh, I guess not, that's a bug, it should stop. The whole thing should stop. And I don't know why it doesn't. I don't remember. So that's a bug in my code that I should fix. Somehow the conveyor motor is still enabled. Oh, I remember what it was. If you happen to hit stop when none of the or when even one of the stations is not finished, and the conveyor, no, it has to be when all the stations are finished. If you happen to hit stop, the conveyor motor will keep going and it will not detect when the bottle sensor goes true. So it's a bug I found that I never got fixed. Anyway, there are some interesting instructions here. I've taught you about some basic things. You recognize this symbol. You recognize this. You probably don't recognize this. This is just a jump instruction. Whenever the runs preceding it are true, it jumps to a subroutine, which is just a different section of code. It's just more ladder logic. The program was Now there are some instructions you probably don't recognize. For example, this add instruction, but you can guess what that is. It's simply adding 2 numbers together, and I'll demonstrate that for you in just a minute. Because if you think about it, you have to count up how many bottles have gone by that are small and that are large, because you have to display that information. Also, you have to keep track of how much glass has been added to the box. And it turns out that a small broken bottle will add less glass to the box than a large broken bottle. You got to figure out how much a box would be able to hold, and then keep track of how much glass is entered the box, so you know when to index the box. Anyway, what else is interesting? Oh yeah, there are some bit shift instructions, and let me see, I don't remember. Here's some comparison instructions. You recognize those from the traffic light. Greater than instructions, and where are my bit shift? It has to be associated with indexing, so it should be here. Maybe I'll put that in a subroutine. Let me see if I can find it. Index done. Yeah, here we are. BSR. Bit shift right. If you think about it, you have to somehow keep track of all these bottles and where they are in the system. And using a bunch of single memory locations makes it difficult. But you can set up what's called a bit shift instruction that will, for example, keep a whole word of data. You've got 16 bits. If you think about it, these bits in memory look a lot like those bottles going by on the line. If you could just keep track of, say that this position represents a bottle that's in this location, okay? Or better yet, in this location is broken. If a bottle's in position that represents a broken bottle, you can put a 1 there, okay? And then, as the conveyor indexes, what you really want to do is just shift all these bits down. Now you can choose to shift them right, you can choose to shift them left. I chose to shift right because that looks like the conveyor moving to the right. Okay. And as you continue, each time the conveyor indexes, you just shift all these bits. That's what the bit shift instruction does. It just takes all the bits and moves them down one. Now the bit that's on the end just gets thrown away sometimes. The way I set it up, it actually goes into another location because if you think about it, there's more than 16 bottles along the way that I have to deal with. But there's less than 32, so I only needed 2 words of data. And that way I could keep track of broken bottles as they move. Then I had another section of memory with another 2 words of data where I was keeping track of which bottles were tall versus short. That's an on and off type of thing. And basically I chose to cap based on whether or not the bottle was broken or not. If there was a bottle in position, but it was broken, then don't bother capping it, because it's already gone. It's already gone down here, and there'd be no point in capping a broken bottle anyway. It's not full. It's not worth capping. Okay. What else was that was interesting? That's probably about it. This This is a much bigger program than you're used to seeing. But I'm going to post it to you guys so you can peruse through it and see. So I guess my point in telling you that is that there are a lot of instructions that, you know, some instructions in PLC lingo, I don't know because I don't use them. I haven't used them. I haven't had a need to use them. But usually there are more instructions in PLC than you really need. But there's some situations where particular instructions are very handy to use. You understand those are all comparison instructions. Let me show you how to use these computation instructions. It's really straightforward and simple. And I'll show you some move instructions as well. You've seen some program control with the jump. There's sequence commands, which I'll describe a little bit to you, and others. But anyway, I don't know all of these. Let me make a new file. Let's go back to the I/O simulator. And I'm going to use some compute math instructions to add two numbers together. Now, I'm not going to interact with this initially at all. What I'm going to do is simply put some constants in here and show you how to add numbers. All right, so we're going to build a really simple calculator. Okay? We're going to add two numbers. Let's see, what is 4? Sounds like something my daughter's asking me because she's just learned to count, so now they're trying to teach her how to add. So she's always quizzing me trying to find out what the answer was. So anyway, 4 plus 2. Let's see, actually, 2 over here. Let's put it into memory and n:0. Okay, now you guys know the result should be 6. Let's find out what happens. Download, run. Let's view memory. Let's go to the integers file. Notice I told it to put the result into the integers memory. Right, so here it is. n:0, not surprisingly, equals 46. Doesn't matter what order you add them in, put the 2 here and the 4 here, still come out with 6, and it will still store the result in this destination. You notice it doesn't make sense to put a number in here. It doesn't make sense to put a 6 in here, for example, because all you're really trying to do is add two things and put them into memory somewhere. Now, most of the time, this is not the way you would use the instruction. Most of the time, you would add 2 words of data where you don't know what those words of data are going to be. So, for example, I might add the word of data at I:0, or no, there's no word at I:0. The word at I:1 and the word at I:3. Now, what words of data would those be? Those would be these 2 words of data, because I'm referencing I:1, which is all of these bits, and I:3, which is all of these bits, and it'll interpret those 2 words as numbers, add them together, and put the result in memory at address 0. So let's play with this and see what happens. All right. Download, run. I have to go into memory to see it. I really don't. It's displayed here as well, but I'll pull it over here, pull it up over here so you can see it as well. Okay, so let's change this to that. Now let's see. 1 plus 0 is 1. 1 plus 1 is 2. If I turn on this bit, what will we have? We'll have the 1s, 2, 4, 8's place on. So 8 plus 1 is 9, plus 1 is 10. So as soon as I turn this on, it should give us the result, which is 10. Okay. Now let's turn on a bunch of random bits and see if it's working properly. All right, let's figure out what we've got. The program nicely displays the results over here. So I:1 has 8,547. Let's verify that. Grab your calculators, please. You just go into a calculator on Windows if you want to. And let's figure out the values of these positions. This one's 37. What it is. Anyway, 2 to the 15th here, 2 to the 14th, 2 to the 13th, whatever that is. That's going to bother me. I need to know what that value is. Scientific is fine. So 2 power of 15, 32,768. I couldn't get the 2. So 32,768 is the value of this bit, but the one we're interested in is 13th bit, so 2 to the power of 13 is 8192. If we add up the rest of these, it probably would come out, but like I showed you last time, it's much easier to simply go to program and start typing it in. So we've got a 1. I'm going to do this slowly in case a lot of people miss this in the past. So I just typed in this 1. I'm going to type in 1, 2, 3, 4 zeros, then a 1, then 1, 2, 3, 4 more zeros, a 1, 2 zeros, and a 1. Okay, so you always enter it from most significant to least significant, just like on regular calculators. You want to type in 1,212. You type 1, 2, 1, 2, right? So you type in the 1 for the 1,000 first. You do the same thing here. So 4 zeros, 1, 2, 3, 4. And it'll ignore any leading zeros. Try it on your calculator too, regular calculator. Try typing in 0, 0, 1, 2, 1, 2. It'll ignore all the leading zeros. It's the same thing, it's just fine. So next is a 1, then 1, 2, 3, 4 more zeros. A 1, 2 zeros, a 1. And I just realized I was in decimal and I should have been in binary. So this is actually a huge number. Let me try again. In binary, it was 1, 1, 2, 4, 1, 1, 2, 4, 1, 1, 2. It's when I go to decimal, that's 8457, which is right. We can assume the other one's correct as well. When you add those two together, the result is 10,500. Okay, now let's do something more interesting. Let's make it display our result over here on this output. So what I'm going to do, if I simply take the addition of the two and put it on that output, I can show you a way to do that next. If I do that, it's going to display it in hexadecimal, which most operators obviously would not understand, but let me just demonstrate it for you. So I'm going to take the word of data that's been added, which is at address 0 in the integers file, and I'm going to output that directly onto the display at output 6. There we go. So there it is in hexadecimal. Let's verify that that's correct. So hexadecimal 291A in decimal is 10522, which is what's right here. Now I'd like for the operator to be able to see that. Now obviously there's only 4 digits here, and that's too large a number to display for the operator. So I'm going to turn off one of these significant digits and get something that we could actually display. Let's check and make sure that's displayable. Okay, so clear 91A in decimal is less than 4, well it's 4 digits, it's 2,330. So I can display that with the 4 digits here. So what I'm going to do is instead of using the move command, all the move command does, it doesn't actually move, it copies. So all this did is it copied the binary data from this address and put it in that address. Okay, so it is 2330 when we display it in decimal, but when it was displayed in this output, it displays in hexadecimal. That's not what we want. So let's display it in decimal in the way that an operator could read it. So we'll go to, where are they? Yeah, there we go. It's decimal to binary coded decimal. So now instead of using the move instruction, I'm going to take the memory, or copy the memory at address 0 and put it into output 6. Now I'm going to leave the move instruction in there to demonstrate a point. So let's start off, download, run, and now it displays in decimal exactly what we expected. You might be scratching your head a little bit and saying, yeah, but what's going on here? Because the move instruction looks at this address, copies the data into memory here, so I'd expect to see 2330 here and here. Because this is displaying what is actually going out to output 6. But what's going out to output 6 is 9009, yet what's being shown is 2330. We have to be very careful. It's a mistake to have 2 instructions trying to write the same output. Okay, that'll trip you up more than once in this class. You'll be scratching your head going, well, this line is calculating the output is what I expect, and yet that's not what's being displayed. The output's not on when I expect it to be. Usually that's because there's another line of code somewhere that's overriding it. This line comes after this line, so it overrides what this calculated. Because this is saying, I'm going to take 2330 and I'm going to change it so that when it's displayed on a binary coded decimal display, it will still display 2330. I'm going to transform it from binary to binary coded decimal. Those two are not the same thing. In fact, if you look at the bits in address 0, they do not look like this. Let's look at them and see, verify that. So we change to binary, and sure enough, we'd expect to see a 0, 1, 0, 1, 1. We see a 0, 0, 0, 0, and then some ones. That's because what the 2 decimal instruction is doing is taking these bits in memory at address 0 and changing them to calculate so that when they're displayed on a binary coded decimal display, it comes out as intended. So there's a big difference between binary and binary coded decimal. They're not the same thing. But anyway, this should be a lesson to you. An output coil or anything that writes a whole word of data, whatever comes last is going to overwrite any calculations from before. So you have to be careful about that. I've already had 1 or 2 students say, hey, what's going on with my program? It's not working. And I was able to show them, well, you've got the same output on 2 different lines, which is a mistake. So really, basically, what's happening here is that this line here with the move instruction is working. It's not doing anything really. It's just wasting scans. So now we get the same result. Okay. Any questions so far? Okay. For those of you that are already finished, let's see, wait a second. Is there anything else I wanted to tell you about? Storing memory, I told you about that. Math instructions, I've shown you a little bit of that. The math instructions are pretty easy to interpret. There's really not a whole lot more to be said, except that you've got subtract, multiply, divide. You can take the square root, you can negate a number, take it from positive to negative. But in this class, we're not going to talk hardly at all about negative numbers. But if you want to indicate a negative number in the PLC's memory, you have to have a bit that is reserved to indicate whether the number that you're dealing with is a positive or a negative number. There's a couple of different ways to represent negative numbers in computers and in PLCs. I'm not really focusing on that. Okay? You've got enough to learn with the program. I've already told you about the 2 decimal and from decimal. You can play with these and see how it works. I will warn you, with a multiply instruction, it's pretty easy to overflow the output. What I mean by that, it's pretty easy to come up with 2 relatively small numbers that, when multiplied together, give you a number that cannot be stored in 1/16-bit address. In other words, you come out with a number that's larger than 65535. And when that happens, you get what's called an overflow. There's extra numbers to be added, and we simply don't have room to store them. And depending on the PLC, it may just truncate it. It may just throw away the extra numbers, and then you get a result that doesn't make any sense. Another thing to know with the divide, it's possible when you divide 2 numbers, it's very easy to get things after the decimal place, right? It's easy to get fractions of a number, okay? Well, in this particular PLC, it does not deal with what's called floating point math. It can't save anything after the decimal place. So anything after the decimal place just gets thrown away and keeps the integer portion of the result. Okay, so that's something that's important to know. And using a PLC or any microcontroller or anything that has only integer math, when you're trying to do normal calculations, especially in integration or differentiation or anything like that, it's kind of an art in and of itself. Okay? But we're not going to discuss all that. Right now I want to focus on programming. You've got plenty to look at. We talked about counters. You know what, did I say that counter file? These counting bottles? I don't think I did. I'll have to recreate it. Anyway, I'll recreate it and post it for you guys, and if you're interested, I'll post this add instruction as well. What I'd like to do now, if you finished homework 2, go ahead and look at homework 3, because it's also available. There's a lot of programming work in it, and I expect that to take longer than the last week. Beyond that, there are a couple more things I want to show you about programming. There's state machine programming and sequence machine programming, but I don't want to show you those to you today. You've already had enough. And I want you to start into homework 3 before I show you those. At the end of homework 3, you're asked to do them. Just pause on the last question or so until I've shown you them. There's plenty of work to do in homework 3. What is it? Homework 3 or homework 4? I don't remember. It may not be true. You may be able to get all the way through. Yeah, you can get all the way through homework 3. It's homework 4 you couldn't get all the way through. And there are questions at the first that you won't be able to answer, but I'll address those later. You can do question 4 on how you can accomplish in theory. But I wanna talk about resolution and all that, next class, I don't wanna mess with that right now. Anyway, so I'll say these programs, I'll recreate that kind of program, post it. And then, I'll probably give you guys about 15 to 30 minutes to work on the homework. If you haven't finished homework, you can start homework break. And then what we'll do is take the last 30 minutes or so of the class for brainstorming, because we've had another meeting on this Christmas display project. And unfortunately, the CGT class that we're going to work with does not meet from 6 to 8 like we do on Tuesdays and Thursdays. So I have to figure out a way to have interaction with them and work with them. But what Professor Finnegan and I have decided to do is just go through the brainstorming exercise in class and see what we're going to come up with. I'll tell you the ideas that we've come up with in our meetings. But this is really your all's project. I want it, and we all want it to be something that you guys come up with and think it sounds exciting and it sounds fun. Okay? All right, go ahead and take a 5-minute break. When you come back, work on the homework. I'll come around and help all of you. So imagine some of you have significant questions or need help. And then we'll brainstorm.